Imagine for a second that you have a piece of technology sitting right on your desk that can listen to just 3 seconds of anyone's voice, like maybe a short clip of you talking or a friend or even an actor.
Just 3 seconds.
Literally 3 seconds. You feed that tiny clip into this system, and within moments, it can speak in over 600 different languages, flawlessly mimicking that exact vocal identity.
Which is wild to even think about.
Right. And we're talking about zero robotic glitches, no weird, algorithmic pauses, just perfect, fluent, omnilingual speech that sounds like it was recorded in a professional studio.
I mean, it sounds like the kind of universal translator device you really only see in science fiction. For a long time, generating that many languages with that level of fidelity from such a tiny prompt, it was considered mathematically impossible for a single model.
But it's totally not fiction anymore. Today, we're taking a deep dive into a stack of research that basically shatters that impossible barrier.
Yeah, the engine behind all this is a newly introduced AI model called ParrotSpeech TTS.
Exactly. And we've got the core research paper spread out in front of us right now, along with some incredibly dense architectural diagrams and a few fascinating data visualizations showing things like language distribution charts and error rate scatter plots.
There's a lot to unpack here.
There really is.
Yeah.
So our mission for this deep dive is to figure out the actual mechanisms, the underlying how and why that allow parrot speech to achieve this state-of-the-art text-to-speech capability, especially for languages that barely have any digital footprint at all.
Right. And to really grasp the sheer scale of what scaling to 646 languages actually means, you kind of have to look at the brick wall that previous text-to-speech or TTS systems kept slamming into.
Because older AI voices always sounded a bit, glitchy.
Exactly. For a while now, the industry standard for high-quality voice cloning has relied on what we call non-autoregressive models, specifically discrete token systems.
Okay, break that down for us.
So they generate audio in parallel, which makes them incredibly fast, but they were built on this fundamentally flawed architecture called the two-stage cascaded pipeline.
Which, looking at the diagrams, is essentially a highly technical game of telephone happening inside the computer, right?
That's a perfect analogy, yeah.
Like you type in your text, and in stage one, the AI translates that text into a semantic representation.
Yeah.
It's stripping the text down to its bare bones meaning and basic pronunciation.
Right, like a translator working from a bad summary instead of the original text.
Yeah, and then it hands that summary off to stage two, which is a completely separate acoustic model. And that second model has to somehow turn that basic summary into complex, multi-layered sound waves.
And the problem with that handoff is twofold. First, you suffer from brutal error propagation.
Because mistakes cascade.
Exactly. If that first stage makes even a microscopic mistake in predicting the semantic emphasis of a word, it passes that flawed instruction right down the line.
And the acoustic model in stage two just doesn't know any better.
Right. It has no idea it's working with bad data, so it just bakes that mistake permanently into the final audio.
Which is why you get those weird robotic inflections.
Yeah. And the second big flaw is you have this massive information bottleneck. When stage one compresses the text into that low bitrate semantic summary to make the handoff easier, it basically leaves all the subtle nuance behind.
So it loses the actual human element.
Completely. The rich, fine-grained details of a human voice, like the subtle breathiness at the end of a sentence or the micro-inflections of sarcasm.
Or even just the resonance of the room you're in.
All of that is lost. The semantic summary just isn't rich enough to carry the soul of the voice across the pipeline.
Okay, but that naturally makes you wonder, why did engineers build it that way in the first place? I mean, if putting a middleman in the pipeline inevitably destroys the fidelity of the voice, why wasn't everyone just building single-stage models from the start?
Oh, they certainly tried.
Oh, really?
Yeah. But mapping text directly to multi-codebook acoustic tokens in one giant leap is incredibly difficult. Think of an acoustic token as a microscopic pixel of sound.
Okay.
By itself, it's just a tiny pop or hiss. You need to layer thousands of them together simultaneously to build a voice.
Right.
Historically, when single-stage models tried to jump directly from text to these complex acoustic pixels, they suffered a massive collapse in intelligibility.
Meaning what exactly?
They mumbled, they would slur words, skip entire syllables, and essentially just generate acoustic garbage. They mumbled because they lacked the underlying structure understanding of how language actually works to guide that direct mapping.
So to build a single-stage model that doesn't mumble, the ParrotSpeech team basically had to solve that core understanding gap.
Exactly.
And looking at their architectural diagrams in the paper, they bypass the two-stage pipeline using a single-stage discrete framework with a bidirectional transformer. But the structural foundation isn't actually the magic part here, is it?
No, the magic is how they gave this architecture a brain transplant.
Yes. The LLM initialization. This is the first major trick, and it's fascinating.
It is the mechanism that completely solves the mumbling problem.
They took the pre-trained weights of a large language model, specifically Qwen 3-0.6b, which is an AI designed purely for predicting text, and they used that text brain to initialize their speech model.
Which is a massive leap.
But let's unpack the why here. Because to me, text math and audio math seem completely different. Why does an LLM's ability to predict the next word in a sentence suddenly give a speech model the ability to generate perfectly clear acoustic sound waves?
Well, because beneath the surface, a transformer architecture is actually agnostic to whether it's processing text or audio. It's really just looking for pattern.
Okay, that makes sense.
A large language model has already spent millions of hours reading billions of pages of text. It has fundamentally mapped the deep grammar, syntax, and structural logic of human language right into its neural weights.
So it already knows the rules of the game.
Exactly. When you initialize the TTS backbone with those specific weights, you are handing the speech model a massive pre-existing structural map.
So it doesn't have to learn what a verb is or how a subordinate clause works at the exact same time as trying to learn what a human vocal cord sounds like.
Right. The speech model inherits all of that deep linguistic knowledge before it ever processes a single acoustic token.
Oh, wow.
Yeah, that linguistic capacity acts as an ironclad anchor. When it attempts the incredibly complex leap from a text prompt to an acoustic sound wave, it relies on that deep syntactic map to keep the mapping aligned.
So it doesn't get confused and start skipping syllables because the LLM brain knows what the shape of the word should be.
Exactly. And paired speech is the very first non-autoregressive model to successfully use this text-to-speech initialization to achieve massive gains in intelligibility.
Okay, so the AI has this brilliant, fast-learning, pre-trained brain.
Hmm.
But it still needs to learn how to map that text knowledge to those acoustic sound pixels.
Which brings us to the training process.
Right, the second major innovation in their architecture.
Yeah.
The masking strategy.
Yeah, this is super clever.
So when you train an AI like this, you basically hide or mask pieces of the data and force the AI to guess what's missing. And when it guesses wrong, it updates its math.
Standard machine learning, yeah.
But looking at the visual comparisons in our sources, the old way, which they call soundstorm-style masking, looks very structured. It looks like the engineers are just deleting solid horizontal blocks of acoustic layers one by one.
It's a very rigid layer-by-layer approach to hiding information.
But ParrotSpeech uses something called full codebook random masking, and the diagram for it looks completely unhinged.
It really does.
It's just a chaotic randomized checkerboard.
Yeah.
They are independently and randomly hiding 50% of the data across all 8 acoustic layers simultaneously. Now wait, if you are training a model, why would you make the lesson plan completely chaotic? If I give a student a textbook where I've randomly blacked out every other word on every single page, it feels like I'm making it significantly harder for them to learn the underlying material compared to just, ripping out chapter 4 entirely.
It is counterintuitive. You are making the task more mathematically complex, absolutely. But that specific complexity forces radical efficiency.
How so?
Think of generating audio across 8 layers, like solving a massive 3-dimensional Sudoku puzzle.
Okay, I like that.
In the old, structured way, the AI only computes its loss, meaning it only calculates its mistakes and updates its learning on a single sparse layer at a time. It's trying to solve one flat plane of the Sudoku puzzle while completely ignoring the vertical connections to the other 7 planes.
Oh, so it's blind to the relationships between the layers of sound.
Very blind and very slow to learn. But with full code book random masking, ParrotSpeech punches random holes through the entire 3D puzzle all at once. Because the masking is chaotic across the whole matrix, the model is forced to compute its loss on all 8 acoustic codebooks simultaneously.
Which means it has to look at the whole picture.
Exactly. It forces the AI to realize that solving a missing token on layer 3 gives it the mathematical clue it needs to solve a missing token on layer 7. By computing that loss globally, it learns the intricate relationships between all the different acoustic frequencies at once.
And the paper notes this, makes it 8 times more efficient than per layer masking. It converges on the correct acoustic map vastly faster, and the final audio quality is significantly richer because the layers are deeply intertwined.
Right, the chaotic masking forces the model to work comprehensively, which makes the final output incredibly cohesive.
Okay, so we have a unified single-stage pipeline, we have a text genius LLM brain, and we have a chaotic 3D Sudoku training method that forces hyper-efficient learning.
That's the engine.
But an AI architecture is just an empty engine without fuel, and the fuel here is the data. Lots and lots of messy data.
And this data set is where the sheer ambition of ParrotSpeech really shows. Expanding language coverage is arguably the hardest challenge in TTS right now.
Because they didn't just build a pristine, highly curated studio data set for a dozen popular languages.
No, they went massive.
They cobbled together 581,000 hours of audio across 646 different languages by pulling from 50 wildly different open source data sets.
They actually had to deploy a completely separate speech restoration model just to scrub the background noise and microphone static out of the audio they scraped together.
That is dedication. But looking at the language duration distribution chart in our sources, there is a glaring statistical nightmare here.
Yes, the long-tail data imbalance.
It's huge. On the far left side of the chart, you have the heavy hitters. English has over 100,000 hours of training audio. Cantonese has over 13,000 hours. The model has an ocean of data to learn from for those. But as you follow the chart to the right, it plummets into this incredibly long, thin tail. You get down to a language like Ayacucho Quechua, an indigenous language spoken in the Andes, and there is a total of 0.05 hours of audio.
3 minutes.
3 minutes. How is it supposed to learn a language from 3 minutes?
Well, from a pure machine learning perspective, a standard neural network will look at that distribution and completely ignore Ayacucho Quechua.
Because it doesn't matter to the overall score.
Exactly. The model's primary goal is to minimize its overall global error rate across all 581,000 hours. If it perfects English and Cantonese, its success rate is basically 99.9%. It mathematically does not care if it completely fails at a language that represents 3 minutes of its total curriculum.
So how did they force the AI to care about the 3 minutes?
They instituted a mathematical intervention at the dataset level using a specific language-level resampling formula. They apply a smoothing factor, represented by the mathematical constant beta. If you set beta to 1.0, you are telling the model to keep the natural, wildly unfair distribution. English stays at 100,000 hours. Quechua stays at 3 minutes.
And Quechua gets ignored.
Right. But if you set beta to 0.0, you force a perfectly uniform distribution. You mathematically trick the system into thinking every single language has the exact same amount of data.
But that would ruin English, right? Because English needs more data.
Completely ruins it. Because English is vastly more complex and requires more data exposure to map correctly.
So you have to find a sweet spot.
They empirically set beta to 0.8. This specific formula gently upsamples the low-resource languages. It artificially inflates their presence in the training mix just enough so the model is forced to pay attention and optimize for them.
Without drowning out the big languages.
Oh, exactly. Without drowning out the complex data needed to master English or Mandarin.
Okay, I have to challenge the logic of that upsampling for a second.
Go ahead.
If you have a 3-minute clip of Ayacucho Quechua, and you mathematically inflate it so the model sees it thousands of times more often, aren't you just going to cause massive overfitting? Like the model is just going to memorize the specific background static or the specific breathing pattern of that one single speaker rather than actually learning the language. When you ask it to generate new sentences in Quechua, shouldn't it just sound like a broken record of that one 3-minute clip?
That is exactly what would happen in a traditional model. But this brings us right back to the brilliance of the LLM initialization.
Oh, the brain transplant.
Yes. The speech model isn't learning Quechua from scratch in an isolated vacuum. All 646 languages are sharing the exact same foundational LLM backbone.
So it's using what it learned from English to help it speak Quechua.
Precisely. When the model processes that oversampled 3-minute clip, it relies on the universal phonetic mapping and general audio quality rules it already learned from its 100,000 hours of English.
That is so smart.
It applies the clean speech parameters of the high-resource languages to the vocabulary of the low-resource language. The shared text brain prevents the acoustic overfitting.
Okay, that is genuinely incredible. It's basically structural democratization of AI. It means someone who speaks a language with almost zero digital footprint can utilize the exact same state-of-the-art voice cloning technology that an English speaker just takes for granted.
It's a huge step forward for accessibility.
But being able to pronounce words correctly is really only part of the challenge. Real human speech is messy. It's reactive. Which brings us to what the paper calls its controllability, features the real-world superpowers of parrot speech.
Yeah, the ability to manipulate the acoustic environment and the speaker identity dynamically.
Let's look at the prompt denoising superpower first.
Yeah.
Because in the real world, if I want to clone a voice, I don't have a quiet, soundproof booth. I'm recording a 3-second clip on my phone while walking down the street with the truck driving by.
And normally, if you feed that to a voice cloner, it dutifully clones the rumble of the truck right alongside your vocal cords.
Right. Because older models couldn't disentangle the intrinsic identity of the speaker from the extrinsic acoustic environment. To the AI, it's all just one big block of sound.
Exactly.
But parrot speech introduces a specific instruction token you can type right into your prompt, the denoise token. You can feed it that terrible wind-blown, truck-rumbling cell phone audio, add the token, and the AI mathematically strips away all the background artifacts.
It's almost like magic.
It isolates your core vocal identity and outputs crystal clear, studio-quality speech in your exact voice.
And you can push that control even further. You don't even need a 3-second audio prompt. You can architect a voice entirely from text.
Wait, really?
Yeah. You can explicitly type in parameters for gender, age, pitch, and accent, and the model synthesizes a highly customized, unique vocal identity on the fly.
That's amazing. And it also gives you a manual override for linguistic edge cases, which I find fascinating. Because every language has corner cases that break AI models.
Oh, absolutely.
Like, English has bizarre, unphonetic, specialized jargon. And Chinese has polyphonic characters, words that are written the exact same way but pronounced completely differently depending on the context of the sentence.
And if the model guesses the context wrong, the pronunciation is wrong, and the illusion of human speech instantly shatters.
So ParrotSpeech just lets you remove the guesswork entirely. You can literally inject explicit phonetic transcriptions like pinyin for Chinese or CMU dictionary phones for English directly into the text prompt.
You force the AI to pronounce it exactly as defined.
You can even type in effective cues. You can put a marker for laughter in the middle of a sentence, and the generated voice will seamlessly transition into an organic laugh while speaking.
It's an unprecedented level of deterministic control.
So we've unpacked the mechanics. It has an LLM brain that stops it from mumbling, a chaotic 3D Sudoku masking strategy that accelerates learning, a beta resampling formula that protects endangered languages, and a whole suite of denoising superpowers.
It's a stacked model.
But the real question is, how does this actually stack up against the current titans of the industry?
The researchers ran rigorous tests against major commercial and open source models, systems like 11 Labs, Minimax, and Cozy Voice 3.
The heavy hitters.
Yeah. They evaluated them across English benchmarks, bilingual Chinese-English sets, and the massive 102 language FLIR's benchmark.
And the defining metric here is word error rate, or WER, which just measures how many words the AI slurs, skips, or completely mispronounces. And parrot speech consistently beat the commercial models in both speaker similarity and maintaining a low word error rate.
It performed phenomenally well.
But looking at the data, I keep returning to this one specific scatter plot. It plots the character error rate, the CER, against the amount of training data for those 102 languages.
It reveals a fascinating paradox about how we measure AI performance.
It's completely wild. The chart has these tiny squares representing the original ground truth human recordings that the AI learned from, and it has circles representing the newly generated parrot speech audio. For dozens of languages that had less than 10 hours of global training data, the AI actually achieved a lower character error rate than the humans. The AI circles dip significantly below the human square.
I know, it looks like a mistake at first.
Wait, you're telling me an AI model that trained on just a few hours of audio is somehow mathematically making fewer mistakes speaking a language than a native human speaker?
Yeah.
Make it make sense.
It sounds impossible until you understand the mechanism of the testing environment.
Okay.
The character error rate is calculated by having another AI system, an automatic speech recognition, or ASR model, listen to the audio and transcribe it. It's essentially a machine listening to a machine.
Ah, so the measurement tool is biased toward clean data.
Exactly. When the transcription AI listens to the ground truth human audio, it's dealing with messy reality. Humans mumble, we trail off at the end of sentences, we breathe heavily into the microphone.
Right.
But when the transcription AI listens to parrot speech, It's hearing speech that has been flawlessly synthesized, perfectly standardized, and entirely scrubbed of background noise. The AI isn't necessarily generating better or more authentic human speech.
It's generating speech that is so mathematically clean that the transcription equipment understands it perfectly.
Yes, the average CER across all 102 languages was an astonishing 4.00%.
And it does all of this incredibly fast. On an H20 GPU, measuring the inference speed, which is just how quickly it generates audio, it boasts a real-time factor of 0.0319 for 16 inference steps.
Which is blazing fast.
That means to generate 1 solid second of audio, the AI only needs about 31 milliseconds to process the math. It's creating speech roughly 30 times faster than real-time, completely crushing competitors like Zip Voice.
It is a remarkable piece of engineering, but as with all groundbreaking research, we do have to look at the structural limitations the authors themselves acknowledge.
Right, the reality check. What's holding it back?
First, because they relied entirely on cobbling together 50 open source data sets, the underlying acoustic quality is wildly inconsistent.
Sure.
They prove the architecture works beautifully on messy data, but that messy data places an artificial ceiling on how good the model can sound. If they were to retrain this exact same single-stage LLM architecture purely on highly curated proprietary studio audio, the acoustic fidelity would likely leap forward again.
Because even with their denoising superpowers, you still can't entirely escape the garbage in, garbage out rule of machine learning.
Exactly.
What else?
Well, the inference speed is incredibly fast, but there is a mathematical limitation inherent to discrete space models. In continuous space models where audio generation is treated as a smooth, continuous mathematical gradient, researchers have developed techniques like flow distillation.
What does that do?
Flow distillation essentially takes a multi-step generation process and mathematically distills it down to a single massive jump, which drastically cuts down generation time.
Okay, got it.
Because ParrotSpeech snaps its audio to specific rigid grid points, the discrete tokens, we don't currently have an equivalent mathematical shortcut to distill those inference steps. So there's still a frontier for optimization there.
And the paper also notes it still occasionally struggles with complex mathematical patterns and dense numeric sequences without an external text normalization tool to guide it.
Right. It still needs a little hand-holding with raw math.
But looking at the big picture, the leap forward is undeniable. The researchers tore down the clunky two-stage bottleneck. They transplanted the deep grammatical understanding of a text-based LLM into a speech engine to cure the mumbling problem.
They designed a chaotic 3D Sudoku random masking strategy to force hyper-efficient learning across all acoustic layers simultaneously.
And by tweaking a single mathematical constant, beta, they forced the AI to actually pay attention to a 581,000-hour dataset that spans over 600 languages.
They've created a truly omnilingual architecture that can clone a voice from a noisy 3-second prompt and synthesize perfectly clean speech faster than real time.
It completely redefines the boundaries of accessible speech technology. But as we wrap up this deep dive, there is an implication here for you to think about that goes far beyond just building better virtual assistants or, faster voiceovers. We established that because of the shared LLM backbone, ParrotSpeech can perfectly synthesize and fluently speak a language with less than a single hour of recorded audio in its entire database.
Some languages only had 3 minutes.
Right. It takes almost nothing for the model to capture the phonetic structure. And right now, across the globe, there are hundreds of endangered languages on the very brink of vanishing forever as their last native speakers grow old and pass away.
It's a tragic loss of human history.
And the traditional barrier to saving those languages was that we couldn't gather enough massive data sets to build tools for them. But if an AI architecture only needs a few minutes of audio and a basic phonetic transcription to learn how to speak a language fluently, dynamically, and naturally, what does that mean for how we preserve our history?
Could AI, rather than just being a tool for the future, become the ultimate cultural archive of the past?
Could this specific technology be the mechanism that prevents a language from ever truly going extinct? Something for you to mull over. Until next time.